This video will cover how to calculate some of the performance measurements in a short-term scheduling system. In the Excel file, we have listed 5 different jobs in the order they were received, the processing time for each job, and the due date in terms of the number of days from today that these jobs are due to be completed. We have 5 columns to the right that represent the sequence of the jobs. 1, 2, 3, 4, 5. So our job is to place each of these jobs in a sequence in one of the 5 places. We'll do that by putting a 1 for each job in exactly one of the columns. For instance, if we simply put 1 on the diagonal, that would represent a first-come, first-served sequence. We have job A in the first position, job B in the second position, job C in the third position, job D in the fourth position, and job E in the fifth position. If we wipe those out, we could do a different sequence. For instance, what if we wanted to do the earliest due date sequence, EDD? The earliest due date is B, so we'd put B in the first position. The next due date is for A, so A would be second, D would be third, C would be fourth, and E would be fifth. So the numbers across the top represent the positions in the sequence. Just so that we can see the calculations as we make them, we'll put the first come, first served sequence back in. That just has 1s on the diagonal. What we see down the bottom are that we have column totals. We need each of these column totals to be 1. In other words, we cannot assign anything in any position in the sequence more than one job. We also need the row totals to be 1 because we want to assign each job exactly once. What we need to do to calculate our performance measures is to calculate the process times and the flow times. We want to list the process times across this row in the order that they appear in the sequence. One way we can do that is by using the sum product formula. We take the sum product of the process times with absolute references and the columns of either 1s or 0s with only absolute references on the rows 2 and 6. Very important here not to get the dollar signs on D because we want to copy this formula to the right. This formula essentially has the function of selecting the process time for the job that is chosen to be in position 1 of the sequence. Notice that if we change the first job in the sequence, for instance, what if we reverse the first 2 jobs? Now B is first in the sequence. Now we bring in B's process time. Because there are no absolute references on the column D, we can copy this formula to the right. Now we want to calculate the flow time for the sequence we've selected. The first flow time is just going to be equal to the process time for the first job. From there on out, the flow time will be equal to the prior flow time plus the process time for the current job. And remember, the flow time tells us the time period where the job finished. Now we want to bring in the due date for the current job in the sequence. this formula will basically have the function of selecting a due date from the list for the job that's chosen in column D. The logic is the same as the formula on the process line. We have a sum product with absolute references on column and row, and then we reference column D, but we do not want absolute references on the column because we'd like to copy this formula to the right. Suppose we change the first two jobs in the sequence. Any sequence where the column totals are 1 and the row totals are 1 is a valid sequence. Now we flip the due dates. So it just has the function of selecting the due date for the job we've chosen at that point in the sequence. Now we want to measure the days late. The days late will be calculated by comparing the flow time and the due date. The flow time, the days late cannot be negative. So the days late will be the flow time minus the due date, but if that calculation results in a negative number, we simply want to make 0 the days late. In the case of, in this first case, the flow time is 6 and the due date's 8, so the job is not late at all, so this formula will result in a 0. Other jobs, however, are finishing late in this sequence. Now we're going to just total each of these rows. Down below, we have a place to calculate each of the measurements we can use to compare different sequences. The average flow time is the total flow time divided by the number of jobs. You could also call this the average completion time. The utilization percentage is the total process time divided by the total flow time. The average jobs in Q is just the reciprocal of the utilization. Total flow time divided by total process time. The average days late is the total days late divided by the number of jobs, which in this case is 5. Now we can measure the statistics or the measurements for any sequence. Right now we have a first come, first served sequence. We can easily change this to a shortest processing time sequence by putting B in the first position, D in the second position, A in the third position, C in the fourth position, and E in the fifth position. We know the sequence is valid when we see row totals of 1 and column totals of 1. Each job has been assigned exactly once. Each place in the sequence has been assigned exactly once. So now we see the statistics down below for a shortest processing time sequence, SPT. We can repeat this for any of the sequences and find the measurements. The other thing that we can do with this model is use Solver to find the sequence that optimizes one of the criteria. Any of the measurements can be used as an objective in Solver. All would be minimized except utilization, which would be maximized. Because utilization would be maximized, it's just colored a different color here for the measurements calculated. Let's make the average days late our first objective. We would want to minimize average days late. The changing cells will be the entire grid here of yellow cells. We need some constraints. We need equality constraints on the assignments of the jobs because we want each job assigned exactly once. We also want equality constraints on the assignments of the positions in the sequence, each one assigned exactly once. The last constraint we're going to add is called a binary constraint. I highlight all the changing cells, and in the middle drop-down box, use BIN for binary. A binary changing cell is one that can either be 0 or 1, but take on no other values. This will satisfy the criteria that we're using the changing cells for in this model. I want to leave the solving method as GRG nonlinear. Before I click Solve, I'm going to click Close, save the solver settings, and make one more adjustment. I'm going to use the convention that before I use Solve to find the sequence, I'm always going to start Solver from the same place. When we use the binary constraint, this is what's going to assure that we get consistent results. So my rule is, and what seems to work well, is to start with a 1 in every one of the changing cells. And then Solver will, in effect, see where we want to leave the 1s and what we want to set to 0. So I open Solver back up and click Solve. We minimized in that solution the average days late. What we see is in effect an earliest due date solution that Solver found to accommodate this. The first due date is for B at 6, so that's first in the sequence. The next due date is A, so that's second in the sequence. D is third, C is fourth, and E is fifth. So it turns out that an earliest due date sequence minimizes average days late. It's not necessarily a rule that always occurs, but it did work for this example. You can repeat the solution by first putting 1s back in all the cells, and then changing the criteria. If we wanted to minimize the average flow time, for instance, we would just simply change the objective and click Solve. What we find in this case that minimizes the average flow time is a shortest processing time solution. B is the shortest job and it's in the first position. D is the second shortest in the second position. A is the third shortest. C is 8. D is 9. So it turned out in this case, and it may not be this case for every example, but the SPT solution was one that minimized the average flow time. You can also maximize utilization or minimize average jobs in the queue by simply changing the objective in this way.